The example shown in this video has intermittent y values. Would that affect the procedure? Find it out here in Numerical Solutions 2C Problems. Least squares readily provide the functions in solving for the best fit line. However, there are again two approaches in the solution. But then, whatever approach one decides to use, you should still come up with the exact coefficients for A and B as if you used the other. The first approach is system of equations, and by the name, this uses two equations which should be solved simultaneously. The first consists of the summation of y, which is equated to a, with the summation of x, then add n times b. The second function is the summation of xy as equated to a times the summation of the square of x, plus b times the summation of x. The second approach is named ordinary least squares, and the best fit line literally uses the function y is equal to mx plus b. M, or the slope, is solved with the function n times the summation of xy less the product of the summations of x and y. All of this is divided by the binomial having n times the summation of x squared less the square of the summation of x. The y-intercept is simpler, which is the summation of y minus the slope m times the summation of x upon n. From the last function, the slope is used to determine the y-intercept, which means that you should plug in the exact value of m in order to avoid deviations for the value of b. From the four functions provided, note that n is required, but what is n? This is the number of data points in the set. The problem requires the principle of least squares to determine the best fit line, and the dataset for linear regression contains 10 data points, so n is 10. Starting with the system of equations, the first equation is summation of y is equal to a with the summation of x plus nb. Work on summations to complete this equation, and from the dataset, the summation of x is 120. And that of y is 138.97. So the first equation then becomes 138.97 as equated with 120a plus 10b. For the second equation, being summation of xy as equal to a times the summation of x squared plus b times the summation of x, it is necessary to determine xy and x squared. With an extended table, xy values are 10.5, 43, 66.5, 114.03, 136.5, 200.88, 222.46, 289.17, 365.2, and 481.25. So the total is 1,929.49. Complete the row for x squared too, giving 2, 16, 49, 81, 100, 144, 196, 289, 400, and 625. The total of x squared is 1,904. So the second equation becomes 1,929.49 as equal to 1904a plus 120b. To solve these two equations simultaneously, multiply the first by 12 to have 1,667.64 as equated to 1,440a plus 120b. Then subtract the second equation to eliminate b. This results to negative 261.85 as equal to negative 464a. So a is then taken as 5,237 over 9,280, or 0.5643. After knowing a, solve for b by substituting a as 0.5643 into the first equation, making it 138.97 as equal to 120 of 5,237 upon 9,280 plus 10b. Isolate the term with b to have 71.2502 as equal to 10b, where b is taken as 7.125. So the function for the best fit line is y as equal to 0.5643x plus 7.125. Solving for the best fit line using ordinary least squares is even shorter. So utilizing the slope-intercept function, the slope is computed as the number of data points multiplied by the summation of xy less the summation of x times the summation of y. Divide everything by n times the summation of x squared minus the square of the summation of x. For this example, m is computed as 10 of 1,929.49 less 120 of 138.97. Everything is divided by 10 of 1,904 minus the square of 120. M turns to be 5,237 over 9,280, or simply 0.5643. The y-intercept is then computed from the summation of y minus the slope multiplied by the summation of x. Then everything is divided by the number of data points. B for this example is then 138.97 minus 5,237 over 9,280 times 120, all over 10, giving B of 7.125. The function then comes out the same as previously computed, that is y as equal to 0.5643x plus 7.125. Thus, the change of y values doesn't change anything from the procedure.